Okay, this lesson is called Modeling Periodic Behavior. And it's your introduction to this, so I'm going to move very slowly through the words that you're going to need here. A function is periodic. I'm in my festive green here. The word here we want is periodic, and that can be a mostly new word to you that we would use the word periodic. So you may not be clear on exactly what that means, but my first definition is it has a pattern of y values that repeats. Ooh, let me underline that in festive green. Repeats at regular intervals. So whatever we're talking about here is going to do the same thing over and over again. You're like, what does that have to do with trig? Well, it has everything to do with trig. So some examples of periodic functions, and I'm not going to get too fancy here with my periodic functions. I'm slow, but I'm learning. Okay, here we go. Oh, that wasn't a straight line, was it? I wanted that to be a straight line. I clicked on straight line. Oh, that's on the pen side of things. Oh, pen, straight line. Yes, green, straight line. No, black, green, straight line. There we go. How did I do it? Still green. Well, we're going to go with green. I'm learning. And I'll make a set of axes. And while I've got it, I'll make another set of axes. I don't want you to read too much into what I'm drawing here. I'm just going, here's what periodic look like. Don't get hung up in what the scale is or why did he draw it higher or lower. None of that. Just here's what periodic ones look like. And in the interest of setting you up for as much success as possible, I'm going to turn that off, then the pen. Is it now a straight line? No, it's still on straight lines. Oh, I'll get some help from my mouse. Turn all that off and go to pen. Okay, good. Here's my first periodic function, and like I say, in the interest of setting you up for success, I'm going to draw one that you're going to get used to. You're going to see a lot of this one. And it's just going to look like a wave. Yeah, just draw that. And that's supposed to repeat itself. That's the big thing, is it just keeps doing the same thing. And you can picture a water wave if you want. Waves are like this. Waves are periodic. The same thing happens over and over and over again. That's what periodic functions are like. I could do something more basic. I could do something that goes, okay, how about like this? Just repeats over and over again. That's all, just very basic introduction to what periodic means. Repeats, basically. How do we know the above examples are functions? Well, they pass the vertical line test. Shh. So while we could make things that are periodic that aren't functions, we'll, of course, in the course called functions, be focused on ones that are functions. There are some periodic functions. Any questions so far? Probably not too much. You're just like, okay, so whatever periodic functions are, there's something that repeats every so often. We need more words. More words coming up. On the graph of a periodic function, oh, I know why that's happening. There we go. On the graph of a periodic function, one complete pattern in the cycle is called a cycle. I gave it away. I already knew what the word was going to be. It's called a cycle. And you can see that in that little graph there. It shows one cycle. So there's a repetitive pattern here. And this might start to look a little familiar. If you've ever seen one of those EKGs or something like that goes, and the little heart monitor goes boop, boop, boop. Very periodic. Your heart beats very periodically. It does the same thing over and over again, mostly. Mostly it changes during the day, but it mostly does something periodic. And this might sort of look like one of those little ECGs. And so the time for each heartbeat, if this was an ECG, which it's not, but at the time for one heartbeat, that is called a cycle. One cycle. There we go. A cycle may begin at any point in the graph. So you don't have to look at the first cycle. You can look at any cycle. Because this is very repetitive, any cycle will do in your analysis. All the cycles are the same in a periodic function. Then you go, well, can't the cycles change? Yes, absolutely. But we won't, the ones we'll look at, we'll mostly study ones that are completely periodic. They don't change as we go along. Certainly your heart changes during the day. If you go to phys ed class, your heart's going to change what it's doing. If you go have a nap, it's going to change what it's doing. And each of those changes we can analyze. But we'll stick to one and just act like your heart beats the same all day, and we'll do that analysis. The horizontal length of one cycle is called the period of the function. That's why it's called periodic, because one cycle is called the period. And the period of the function in the graph above is, first math question. How wide is one cycle? So I got to look at the scale, figure this out. It starts at 1, ends at 5. So this period here is 4. Okay? So the period, if you want, is sometimes called the width, and that's not the perfect word for it, but I accept that. I accept what you're saying when someone says width. It's the width of one cycle. Okay so far? Some new words, but we'll use the words enough, hopefully. Like I'll use them lots tomorrow, and so hopefully you'll get used to the words. More time? Example. Determine whether each of the following is periodic. If it is, state the period. One of these is periodic, and one is not. I've purposely chosen them in a way to try to fool you a little bit, to make you really think about the definitions. Which one is clearly periodic? B clearly is periodic because it repeats and does the same thing over and over again. In fact, I'll highlight in green one complete cycle. I can start at the beginning. I don't have to, but I can. And there's one complete cycle. See, after that little W, it just does more and more W's. I didn't really see the letter W until I drew it on there, but it's just repeating the same thing. So this is periodic because it does the same exact thing over and over again. And meanwhile, hopefully you're thinking about why the one on the left isn't periodic. Even though it sort of looks like it might be, it's not. And then we want the period, and it's really helpful to highlight one full cycle when you're first learning about these, because it really helps to find the period. And I said you don't have to start at 0 for a cycle, but if you can, it really makes it easy, because then you can really see what the period is here. And the period is 8. That's the width of one cycle. That's how long it takes to repeat. Well, I've already said it out loud. A is not periodic. Can anyone tell me, using the words I've done so far, what is it about this thing that makes it not periodic, even though it looks sort of repetitive?
It's not truly repeating itself. It's increasing value.
Yeah, it's not going back to the same y values again and again, is it? Yeah. So I'll say not periodic. This one over here, not periodic. And I loved what she said, but I will say it very quickly, in very few words. Y values don't repeat. Can you hear me saying shh? Can you hear that? Because you just keep going after I said shh.
Oh, you're talking to me?
Do you see anyone else talking?
Yeah, you were.
Thank you. She said it better than I did, but I tried to say it briefly. Y values don't repeat. Really get to the definition there. Do you have any questions? Sometimes the nice thing about new words and new definitions is it's actually pretty straightforward, lessons like this. It's not too complicated. Can't get too crazy here because the definitions are brand new. So this says determine the period of the function in the following graph and then find each of the following values. So the period, again, you may find it helpful to start at 0 if you can. It's not always easy to start at 0 because maybe that's in the middle of a cycle. and highlight one cycle like that, because that might really help you decide what the period is. And the period here is 7. It goes from 0 to 7. And then it asks for a couple of function values. This should be pretty straightforward. The function value at 6, and I'm challenging myself here to change colors, okay? Because I'm just learning with this pen. I'm going to switch to red. Does it? You think it is red? I don't know. We'll see. At 6. Oh, it is. There it is. It's -1. Okay? Now, challenging question here. So wake up if you've fallen asleep. This is the kind of periodic question we ask. We say f at 20, and what do you notice is the problem with finding f at 20? You can probably do it. You can figure it out. I'm not saying it can't be done. I'm just saying there is a problem here. The graph doesn't go out to 20. So we got to use the period.
But if every period's 7 and the 6 is before the 7 and the 20 is before the 21, then it'll be -1.
I think I know what you're saying. He's saying, oh, I can map it backwards. I can figure out, well, if they want f at 20 and the period 7, that'll be the same as f at 13. That's not exactly what he said, but I'm doing something I hope will help in other questions, whereas I'm saying, okay, well, because the period is 20, I know f at 20 is the same as f at 13. Does that help me? And look at my graph, and there it is. Yes, f at 13, I can find that on the graph. You might have to go more times than that, but that worked out, that I could find that by just using the period to map backwards. And we'll do a lot of that type of thinking in this chapter where we go. We can use the periodic nature to make predictions about what's going to happen later. This is how they know. This is exactly how they know how many hours of sunlight there'll be on each day of the year, and exactly how they know virtually everything about weather on the planet, because they know exactly what's going to happen in the future, because the Earth just keeps doing the same thing over and over again, generally. There's changes, of course. Like this year, doesn't look like any snow for Christmas this year. Yeah? But I can remember years. Do you remember years where it was like, by now I was already skating on my back pond. Like it was cold enough that the pond was already frozen. So there is changes, but the basic nature of sunlight doesn't actually change year to year. Okay, questions there? Is it okay so far? I got one more new word to show you. In any periodic function, the amplitude, have you heard this word before? Amplitude. It's mentioned in science a lot, and you might have, anytime you talk about an amplifier, that's exactly what we're talking about. We're changing the amplitude of the waves. We're making the waves bigger. So the amplitude of the function is defined as half the difference between the max and the min. Now, some people don't like that definition. They go, why would you make it half? And you'll just have to let time go by where you realize, oh, that's why we made it half. We just want the height of the up as opposed to down. And when we do word problems in a couple days, you'll see, oh, that makes a lot of sense why we chose half. For now, you just got to play along and go, that seems a little ridiculous that you choose half the height. Why wouldn't we just use the whole height? Isn't that easier? There's some very good reasons why we want half the height, and we'll get to them very soon. Maybe I do have an example. If I push my daughter Chloe on the swing, yeah, I'm just pushing her on the swing. I'm saying, what height is she getting to? She's going to find her height from the middle, not from the other side. She's only going to find half. Yeah? That's not a great example, but it sort of gives you a hint why we only want to talk about half the height. Anyways, find the whole height of the wave. I'm already calling them waves because I know where all this stuff is going. Lots of talk about waves. You're like, why do we care about waves? Waves are everything. Unfortunately, I got to tell you, waves are everything. Microwaves, X-rays, water waves, light waves, sound waves, electron waves, gravity waves, it's all waves. And so this is the beginning of the analysis of waves. Anyways, this whole height here is, you could just count it. You could do that. 1, 2, 3, 4. Yes. I'm going to do something slightly different, not to mess you up, just to, in the future, you might want to do something like this, where you go, oh, the height is 3 minus -1, which is the 4. And if you think I'm just messing you up, then just ignore me. Just go, why are you doing that? Just I can just count it. I'm like, I know. If you don't have the graph, you might want a method. And the method is take the top, subtract the bottom, and you'll get the height of the wave. But that's not the amplitude. Here's a helpful little move. Amplitude is the height divided by 2 for some reason. Given one sort of example. Sort of example. It's not a great example. I'll do better. I'll do better. Before the week is out. Before you go home on Friday. I'll do better about amplitude. But for now, amplitude is you find the whole height and then you divide by 2. So the amplitude is 2. It's basically how far from the middle did you get? Yeah, how far from the center did you get? And what we'll do is we'll draw these center lines on later. And we'll say, how far from the center did you get? And you got 2 from the center, so your amplitude's 2. I'm giving it away a little bit. Okay, we don't need all that today, but I'm just telling you why we use amplitude as half the height. Are you okay so far? Just some words, and use these notes. I'm not saying don't text or email me. I'm just saying the notes really explain a lot of the words you're looking for here if you just look back. More time here. Challenging myself to get good with this pen. Which clearly I'm not getting good with it. So every time I get a chance to edit or change, that's what I'm going to do. All right. More time there? So the amplitude and period of a periodic function are always positive numbers. We'll always take the positive version of that. And it reminds me of measuring length and width of rectangles. We always look at it and go, let's just use the positive numbers. On the graph of a periodic function, the amplitude is a horizontal measurement. And maybe that word triggers you a little bit to go, oh, maybe I know what's coming here. Transformations is on the way. Yes? And the period is a vertical measurement. More on that tomorrow. I just mentioned it, sort of like, what do they call it in English? A little foreshadowing there of what's coming next. Yes? I see what the problem is here. See when I put the pen over here? It's trying to do something cool and let me do something weird here, but I don't want to do that, and it's messing me up there. You don't care. All right. Last page. More time? Actual example. Starting to move towards things we'd actually do. Andre is jogging on a straight boardwalk beside the ocean. The boardwalk is 800 meters long, and Andre begins jogging from one end at a steady pace of 8 kilometers per hour. Graph Andre's distance in meters from the starting point versus time in minutes for 4 lengths of the boardwalk. All right, lots going on here, but the first thing I want to mention is this is a periodic situation. Andre's going to run to the end of the boardwalk, and then he's going to run back. Then he's going to run to the end of the boardwalk, and then he's going to run back. It's going to be very repetitive. First question. How far is the farthest Andre gets away from where he started? If the boardwalk's 800 meters long. 800 meters. Okay? So that's what he's got to get to here. So I'm going to put on here, I'm going to go, how many squares I got? 1, 2, 3, 4, 5, 6. Oh, that's not going to go well. So I'm going to go 200, 400, 600, 800. Oops, my 400 didn't go very well there. So these are the distance in meters. Anybody taking physics right now? Yeah? I probably should say displacement, but I don't want to mess anyone up here. So we'll just still say distance from the start. It's okay. I'm phrasing it okay, physics people. We'll survive. Distance from his starting point. Now, this is difficult. 800 meters long, and he's going 8 kilometers per hour. So I'll do it the non-physicsy way. I won't get carried away here with physics. I'll just do a little thinking here and go, if he's going 8 kilometers per hour, then he's doing 8,000 meters in 1 hour. I did that little measurement conversion here, 8,000 meters in 1 hour. So to do 800 meters, divide it by 10. So take 1 hour and divide it by 10.
Transfer it to minutes.
Wouldn't minutes be better here? Yes, I agree. We could go tenths of an hour. I don't think so. We will do 60 minutes divided by 10. Sorry. Yeah, 60 minutes divided by 10. So it's 6 minutes it takes him to get to the end of the pier. That's the non-physicsy way. I could break out a formula, but I think that's the way to think it out if you're not sure on these things go. Let me just think about this for a second. He's gone 8,000 meters an hour. So to go 800 meters, that takes him 1/10 of an hour. And 1/10 of an hour is 6 minutes. Okay? So my scale here, I got to go, it takes him 6 minutes, 4 lengths of the boardwalk. Okay, any swimmers in the crowd here? No competitive swimmers? Usually we have one competitive swimmer. The length, when you're doing lengths of the pool, how do you count lengths? Like, do you get a length from going from here to the other end, or do you got to go there and back? Just there. Okay? I think that's the way he's probably going to count too. A length there and a length back. For you swimmers, you're like, no, a length is there and back. I am with you. Doesn't happen to be a swimming example. I'm not trying to change the rules. So he's going to take 6 minutes to get to the other end. And we want to do 4 lengths. So I don't know, 2, 4, 6, 8, 10, 12, 14, 16, 18, 20. Okay, that seems to work. There's 6 minutes. Oh, that was my hand that did that. Silly touchscreen. 6, 12, 18, 24. I think I've done that right. Every third square. This is minutes. And now I'll try and switch to blue here. Oh, that went well. Ooh, I'll try and switch to straight line blue. Really trying to challenge myself here. Straight line blue. So it takes him, doesn't it look like I'm on straight line blue? No. Sorry for the delay, but I've got to challenge myself here.
8 kilometers is 8,000 meters.
8 kilometers is 8,000 meters, yes. Totally cheating here and doing what I said I wouldn't do. Why does he get back down to 0? It's a great question.
Can I just keep going up?
Doesn't it just keep going up? Yeah. No. I'll read the question again for you in just a second. Here, this is what somebody's asking. His distance from the starting point. So when he gets back to the start of the pier, his distance from the starting point is back to 0. You physics people are like, oh, this is why we need another word. We use the word displacement and then we don't have to worry about all this. Yeah? But not everyone's taken physics yet, which you should. It's a great course. Determine the period and the amplitude. Period. How long does it take him to get back to his starting point?
You just spit on me, boss. You spat on me.
12 minutes. Amplitude is half the height. And this is a great example to question and go, why would we do half the height? You're just going to have to trust me that half the height is the way to go for the word amplitude. We've got two words available. Height's the height of the whole wave, and amplitude is half that. Domain and range. I think the range is the easier one here.
Domain is just the element of reals, right?
It's x element of reals
And
and
y
y
is
is
greater than 0.
but less than 800.
Yeah, for me, the range, maybe not easier to write, but easier to talk about. 0 to 800, that's just his range. Now the domain comes down to how we understand the question. Is he going to jog forever?
Yes.
Well, it depends on who he is.
Yeah, it doesn't really say. And if it was phrased this way on a test, you could say, Mr. Todd, does he keep jogging forever? They're in the question of saying 4 lengths of the boardwalk. So that's what I'm going to use for my domain, is the 4 lengths we're talking about here. So the domain is x element of reals such that 0 is less than or equal to x is less than or equal to 24. And you could argue if you want, and I would agree with you, that this question hasn't made it real clear whether he's going to jog forever or stop after his 4 lengths. Okay, so I did 4 lengths. Any questions there? That's what's your homework. Those are the type of questions your homework will look at. For 7.2. Now listen, what I did in the homework is I copied 7.1, which just redoes some stuff from previous chapter. It's just extra practice if you had trouble with those type of questions. So you can look at 7.1 and go, totally going to skip it. I feel good about that stuff, no problem. Or you can use that if you need to repractice any of some of the stuff from chapter 6. So it's like a review of chapter 7. So we're actually talking about 7.2 here. This is the lesson for 7.2. So you get to skip a section there. Now, if you flip to your next sheet, I'm going to start your little investigation for you. Yes? And here's the investigation of the chapter that you can hand in for marks, this back page. I know it's stapled together, but you can hand in the back page for marks. Later in the chapter, I want you to have it. You're going to need this for tomorrow. So this is an important part of the homework, is to do this investigation. And you're like, how am I going to know it's right? Well, like previous chapters, as I'm teaching tomorrow, I'll mention things in the investigation. Have your investigation out tomorrow. And you'll be like, and then I'll say something like, oh, it should have come out like this, and you'll be able to compare with what you had. I'll start it for you right now. Select the investigation, and let me show you what has to happen here. It says, complete the following table values for sine x. And it says, find sine of 0. So I go sine 0. And I get 0. And if you're freaking out a little bit, like, wait a minute, we're going to have a graph of sine x in a minute? The answer is yeah, and wait till you see what it looks like. I'm not going to spoil it. I'm not going to do enough to spoil it for you. Easy to check, too. You could totally type this into the internet. Don't do it. Do the investigation first. See what you get, then type it in to check, or bring it to me to check. So I'll do just a couple more. All you have to do on the table is go, get your calculator, sine 30. And if your calculator gives the fancy answer, get it as decimal. So you can graph it this time, 0.5. And that's all I'm going to do for your investigation.
Did you put it in the calculator?
Shouldn't take long. You can graph all the dots, and you can see what sine looks like. As it happens, hopefully you'll go, oh, I see why it's with this lesson. Okay? Then there's some questions to answer about sine. Then there's do it all again for cos.
Sure, yes, sir.
No tan. Well, no, it's just bad for your skin.
Yep.
there's some specific reasons why no tan. We'll just do sine and cos for now. Tan gets a little crazy. Sine and cos are nice. You'll like them. I promise you'll like them. As it's happening, you're like, whoa, this is cool. Don't look it up first. Do it yourself and then look it up afterwards, okay? Any questions about all that? So you got homework and an investigation. You really want to get them both done for tomorrow's lesson.